This is NEAF Talks.
And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Hey, thank you. Welcome back and good afternoon, everybody. Our next speaker is a science visual developer at the Space Telescope Science Institute. She's leveraging art and science in creating incredible imaging from the raw data from the Webb telescope and other imaging sources. But to get that raw data from the gray, black, and white format into these unbelievable images that is very useful in both science and just the public imaging that we've already seen is a rather involved process. I got to see her, I don't know if many of you may have saw her, she was on 60 Minutes this past Sunday night and gave an incredible, there were incredible shots they show us. Please join me in welcoming to NEAF 2023, image specialist Alyssa Pagan, as she discusses the art and science of translating infrared data into amazing, really amazing images.
Hi everyone, thank you for joining me today. This is my first time on this awesome stage. It's such a privilege, it's such an honor, and my first time being at this conference. So I met a lot of you people, wonderful, do a lot for sort of the astro community. So I'm going to talk to you a little bit of how we create imagery, Webb Imagery specifically. I am a science visuals developer, and all that means is that I take astronomical data from observatories like Webb, like Hubble, and other telescopes, and create color imagery that complement science releases or news releases, education products, and other outreach resources. But before I get too far into how we process the imagery, it's kind of nice to look back, reflect back, and see how far we come. Like, how did we get here? So Webb was over 25 years in the making, a huge project, lots of hands involved, scientists, engineers. Actually, at the conference, the NEAF conference, a lot of people were coming to me talking about how they know someone or an institute that was working on the mirrors, working on different instruments, the engineering. Just an incredible feat of human nature to build this telescope. And it's nice to look back, see how far we've come, and appreciate the significance of the data that we're seeing, and also understanding the instruments helps us understand what we're seeing in the images as well. Okay, so I'm not going to go too far back to conception, but I do want to go back to launch day. And so this was Christmas Day 2021, 7:20 a.m. early. How many people watched the launch that day? Okay, a lot of you. So I was on the couch with my PJs. You might have been doing the same, eating breakfast, probably getting up earlier than the kids, which is probably rare on a Christmas day. But very exciting times. It was launching by an Ariane 5 rocket in French Guiana. So in case you missed the launch, though, I can show you a little video of that launch.
Top, à Jérôme, 1 minute.
Thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 30 seconds and counting. Standing by for terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
Trajectoire est nominale.
And let's go down to the floor in the Jupiter Control Center to Raphael Chevrier of Arianespace. Raphael, so far so good.
Hi, Rob. So far so good. Everything is nominal.
We're done, right? We're good to go. Nothing to worry about. No, so this is where the real work begins. Not that that wasn't difficult work. We have to unfold this telescope in space, because as you may know, James Webb has got a 6.5 primary mirror that has to unfold. It has a tennis court-sized sun shield that has 5 layers that has to unfold, and it has to tense, and then it also has these struts that have to unfold. So there's a lot of things that could go wrong here, and while it's doing that, while it's deploying, it's traveling to its resting point 1 million miles away from Earth. So a lot of things to be worried about. So we have, again, 178 release devices, we've got 50 deployable structures, and all that has to happen exactly as so for it to be fully successful. So you can think about over 344 points of failure. So if one of those single things go wrong, it's done. The mission is done. And that's just crazy to think about now. Luckily, I didn't know these statistics beforehand, or else I'd be kind of chomping at the bit here. But again, we're deploying this telescope. It's unfolding. So that's including the mirror and the struts. We have to align the mirrors. We have to calibrate the instruments. And we also have to cool the instruments, because this is an infrared telescope. And we have to cool it very slowly, or else we can form ice on the instruments, which could cause problems. So you can see this is like a huge endeavor, and this is the point where Space Telescope Science Institute takes control in the mission's operations center. So Webb is considered the successor to Spitzer and Hubble, but it's not a replacement. It's working together in tandem. And this is just a nice look at the unexpected near-cam selfie that we got. None of us were really expecting this. It was just sort of hidden pupil camera that's able to see and sanity check the mirror and make sure it's aligned. Of course, there's more rigorous ways to find that out. But it's a nice way to see James Webb so far away from us. And it's important to kind of look at this because it actually is showcasing you why we're getting, or what we're seeing, why we're seeing. So in case of like Webb's unique stars, for instance, we have this point spread function that happens. And you might have noticed in Webb Imagery, we have these 8 spikes, and where do they come from? And that's just these light is diffracting off of the telescope, these individual hexagonal mirrors. So that's where you get the 6 spikes, and then you get that horizontal spike by the 3 struts that are holding the secondary mirror. And as you can see, that's what you get when we get the imagery. So it's all sort of predicted and modeled. And we get a little bit extra also. We have these background galaxies. This was just an alignment evaluation image, but we got a little bit more bang for our buck here. So we'll find that there's going to be a lot of background galaxies in Webb Imagery. And this is just a look at these different instruments. Of course, I'm talking about the imaging and observing modes, imaging modes, in general. But there's so many different modes that are so important to Webb and the science that we're doing. So I definitely don't want to neglect those. We'll be focusing on the near-infrared camera and the mid-infrared camera mostly, because the near-infrared camera has the highest resolution imagery, which is the focus of the talk today. But again, these are all essential to Webb's operations and discovering so many things, especially spectra. Webb will be taking spectra, and it's very good at that. It's good at breaking down component colors of light, which acts as like a barcode to the object that we're looking at. So we get an understanding about lots of the object's attributes as well as like chemical composition. Okay, so why do we care about infrared light? Why do we need a telescope like Webb? So this is the electromagnetic spectrum that you can see here. We only see a very small part of the electromagnetic spectrum, the visible light. On the left hand, we have the longer wavelengths, the radio waves, the lower energy. On the right hand, we have the shorter wavelengths, the higher energy, so like your UV, your X-rays. But as you can see here, if we only understood what we could see, we'd be missing out on over 90% of what's out there. And our understanding of the universe will be very, very limited. And also, a lot of the technology we use today, we wouldn't be able to. So using your cell phones, turning on the TV, heating up your food in the microwave, all these things we use right now, and we want to apply that also to space and broaden our understanding of space. So this is a sci-fi example here. We got the predator. He can see in infrared. That's what makes him, so deadly. And a lot of other predators actually can see in infrared light too to kind of leverage seeing their prey. And of course, I hate to break it to y'all, I don't think Arnold Schwarzenegger would be able to hide from the predator covered in mud. I think the infrared light would give him away. But this is another more realistic technology that we have, which is, we have face mapping to unlock our phones, and this is just infrared points that are put on our face that we're able to do that for. And then applying this to space, we have this bag on the right, which is opaque. We can't see through the bag. But on the right, we can see the scientist's hand through the bag using an infrared camera. You can see the hottest spots are the yellow and the white, and the cooler spots are emanating in this blue and sort of purple region. And if we point a camera to like a spiral galaxy and we're observing it in visible light and we're observing it in infrared light, we're also going to get a completely different picture. So visible light here is giving us a picture of a galaxy that we're kind of used to. We have this dusty core, we have this hot stars, and we have this sort of dark dust lanes that seem to disappear in this other image of infrared light. This is the mid-infrared camera. So not only is it looking through gas and dust, it's actually seeing it emanate. So it's like the cooler dust we can actually see. So it's almost like an inverse of the galaxy. It's the bones of the galaxy. And that's why it's so important to see in these different wavelengths of light. And another concept that's really important that Webb is going to help us do is see even further back in time, see some of the youngest stars and galaxies. And that's because of a concept known as cosmological redshift. So all that means is over time, space is expanding. If you have a galaxy that's really far away and the light's traveling to you, that light gets stretched out. And that gets redshifted, so it appears in the infrared part of the spectrum, which Webb can pick up. So we're able to detect these far, far galaxies and these distant stars. And of course, all to do that, it has to be above the atmosphere because the atmosphere absorbs infrared. Also, there's other benefits to having space telescopes because you don't have any issues with seeing, so you don't have to deal with the atmosphere. Very nice for observing. And again, I mentioned before, even though Webb is considered the successor to Hubble and Spitzer, Hubble is still out there doing a lot of data, and they're working together in tandem to give us a full picture and perspective of our universe. Just the same way that we utilize different medical equipment to understand our bodies better, like we have X-ray machines to see our bones, and then we have like MRIs to see our soft tissue. It's the same deal, just getting a full understanding. Okay, so just a brief look at some of the images that have come out and showcasing some of the things that what Webb was designed to do. Now, that's not to say that even though we had some questions in mind that Webb was supposed to solve, we'll probably get answers to things that we didn't have questions for. But this is just some of the first things that we've gotten back. So this is the Pandora cluster. So this is a deep field image, and these are really important because with Webb's capabilities, we're able to see some of the furthest galaxies. So this is one of the deepest fields that we have. But it's not actually a very long exposure time, but it's able to do that with infrared. And we also, because it's a cluster, it's bending the light, it's warping space so that we're able to magnify things that are even further behind it, maximizing basically what Webb can see. So it's really nice to look at these things. You can kind of see some streaks over there near the clusters, and those are background galaxies that we can study really well. And this is just a diagram showing how that works with a galaxy in the back, and then space is being bent by these really massive clusters, and then we get to see these galaxies in fine detail that are so far away. Okay, and then we're kind of starting like in the early universe, and now we're getting a little bit closer to us. This is galaxies. This is Stephan's quintet, which is actually a bit of a misnomer. Technically, it's a quartet, because that guy in the front, that bluer galaxy, that's actually closer to us. So it's like 40 million light years away versus like 290 million light years away, which is what the major cluster is, the 4 galaxies are. And it's important to look at these galaxies that are interacting because it helps us basically understand how galaxies evolve, how these interactions influence how they develop over time, as well as how their supermassive black holes influence how they develop. Just like on the top right, we have a galaxy that you can kind of see in the mid-infrared, which has a supermassive black hole. And so from left to right, we have a Hubble image. In the middle, we have the near-infrared image. And then we have the mid-infrared combined with the near-cam image. So we're getting the addition of seeing through the gas and dust, but also seeing some of the dust emit. So you can look back at the Hubble image, and things that were being like with dark dust lanes is like lighting up, showing us how the dust is interacting. And this is helpful for our understanding of how our universe, or how our galaxy, the Milky Way, is developing. And then we have this iconic image, the Pillars of Creation, very famous Hubble image, and we're looking at it again in the Webb. But in this case, this is a composite image again of the mid-infrared instrument and the near-infrared instrument. So we get the benefit of seeing both things happening here. We have these sort of regions of really red stars, so you can see through the dust, and you can also emits a bit. So, but you can see there's areas, what we call lava pools, or these embedded stars that we wouldn't be able to see that are sort of cocooned in this dust. And this is really important to understanding sort of the different stages of stars, which are very important to life, and basically they speak to our origins. So if we understand star development, star birth, and star death, we're understanding how we came to be, how our planets and our solar system came to be. So it's the universe looking back at itself, essentially. And then, so on the other scale, or the other side of the spectrum, we have star death. So this is Cassiopeia A, and this is a stellar, or this is a supernova remnant. So this is a star that died about 340 years ago, which is not very long at all. It's the youngest one that we know. And we get a lot of information here about the heavy elements that are emitting in sort of this pink and yellow-white color. And then we also have some emission here of the dust from the shock wave, the impact of the shock wave hitting that dust around it. So again, this really helps us understanding, fill the gaps of stellar evolution, how it develops, and see the origins of everything, essentially. And I would be remiss to not talk about spectra, even though we're focusing on imaging. A lot of what Webb do relies on spectra. So again, spectra is just when you take light, you break it down into component colors so you can start seeing things like composition. And this is really important for things like exoplanets, planets that are out of our solar system. And we can detect with very good clarity and refinement with Webb these exoplanets using these transient light curves. So we look at a star, the exoplanet passes in front of it, and then there's a dip in the light curve, and so we know we've detected something. And we can also measure the atmosphere or get light from the atmosphere in order to determine its composition. And then we can look at things like possibilities of life or habitability. They look for things like water and carbon dioxide. And then we also can directly image exoplanets, which is something that Webb can do very well. And it's crazy. This is exoplanet HIP 65426b, not a very significant name, but very significant exoplanet that was detected. This was the first exoplanet that was detected by Webb. And what makes it so hard to do is Webb is so sensitive that it is able to detect this exoplanet that's 10,000 times dimmer than its host star. That's crazy, 10,000 times dimmer. But Webb is able to do that with such clarity with this coronagraph instrument. And Webb can do more of just the same. And then, of course, in our own solar system, so we started way far, and now we're getting close to us. This is Uranus. And so I apologize for the ratio. Everything's a little squished. But this is Uranus, and it's seen in unprecedented detail. So the rings here are seen. They're the best view that we've seen since Voyager. So incredible what's coming here. And also, we're revealing this, just all these background stars, or background galaxies, I should say, in this wide field image here that you would never see. We're not used to seeing that when we're looking at solar system objects, but Webb captures that, even in those. Okay, so why do we make color images in the first place? Like, why do we care? Well, the first thing is we want to visualize the data. So, numerical information is really important for data analysis and research and science, but if we just want to get a big picture understanding of what's happening, we need to see it. And it's better to see it all at once with all the separate wavelengths and all together. And then we also want to share or illustrate these scientific discoveries. And we want to disseminate it to everyone. We don't want just scientists to appreciate it. We want everyone to be able to understand it at any scientific literacy. And sort of these images help as a gateway to that science. And that ties into engaging the public, because we want people to be excited about astronomy. We want people to get interested in astronomy and hopefully inspire a whole generation of new scientists and engineers. And this is just showing you sort of the power of this imagery here. I went too fast. But These are first pages of all of these articles that you see here of the first images that were released on July 12th. So this is over 150 articles about it in the New York Times, etc. Getting people involved, reaching a lot of people, making astronomy more mainstream, which is exactly what we want to do. Get people asking questions. Also, the first images that were displayed in July 12th were also in Times Square. And over 300,000 people are walking there all the time, looking up and getting to see these, even Spectra, which is crazy. We don't usually show off the Spectra, poor Spectra. But we also have a Google Doodle, which reached over 50,000 countries, not 50 countries. I'm trying to add more countries. But there's a lot of countries. But yes, it's just like widespread. These images are able to go a lot further than maybe just a science article, and that's what we want. This is the first page of the Time, or the cover of the Times. This is photos of the year. This is the deep field image that Webb observed that was shown like a day before the first images were released by the president. So that got like a lot of excitement and people getting involved. Okay, so I'm going to start to get into the processing. Very briefly, I'm going to talk about sort of the pre-processing stage, or the observing stage, things that we have to do, like planning before we even do it. So this is not something that I partake in too much, but I am usually part of sort of a group of people that design these observations. So we have to think about, the time of year, because only certain things are visible during the year. We have to think about tiles, because this is a mosaic, so we have to have several pointings, because Webb has, a pretty narrow field of view, but that's why it has such high resolutions. But we want to get like a nice large field. We have to think about exposure time. We have to think about specific filters, so different wavelength ranges that are showing us something about this object. So all those things we have to consider. And this looks a little funky. You may not know what this image is, but you probably have seen it. And this is actually the Carina Nebula. So there's a lot of planning that goes into that. And that's actually just, as you saw, it's made out of a lot of different tiles. This is just one tile or one observation that's part of a larger mosaic here. And I'm not going to go into it too specifically, but this is just the pre-processing stuff. And so we start with this one tile here. This is the beginning stage, and it goes really quickly, but it's just groups that are collecting light. So I'm going to go back a little bit again so you can see it. It's just signal that's being built. Raw data. And you can see there's a lot of artifacts there. That's from the detector. And that's going to get removed in the next stage. And so we've done that. We removed it, and at this stage we also start flagging things like dead pixels, saturated things, just pixels that need to be corrected later on and filled in with other data. And then we apply sort of the coordinate system that we use. We calibrate the image fully, and then it's distortion corrected, and that's just because of the angle of the instruments to the secondary mirror, the light that's coming in. But then after all that, we have to do that for every single tile and then piece it all together. And then we finally get one image and one filter. Okay, so I'm a little ahead of myself, so let's get to the actual post-processing, the part that I really start taking over. And this is actually the image of a Carina Nebula. Can you see anything? So there's actually some faint stars in there. The reason why it looks like this straight from the telescope is because of something that we have to do called stretching. This telescope is so sensitive to light that it has such a high dynamic range. So there's just so much information here, and we have to scale it appropriately in order to see it on our screens. So again, we have another image, and this is actually the Webb Deep Field that you saw on the cover of the Time magazine. This is the 2.7 micron filter. So just one specific wavelength range of light. And again, we have to do something called stretching. So you can see the histogram here on my left, and we can see that those pixels are sort of scrunched up to the left, or my left. Your left too. Okay, good. And we need to stretch them out so that we can see them, because we want to be able to make out those faint details that are near the background level, and that's exactly what we're going to do. We're just going to scale those brightness values. And so we're going to take a look at doing this with just a simpler image that only has 4 values, or 2 bits of information. So it has black, dark gray, light gray, and white. And so there's a couple things that we can do. This first one example is just linear. It's just 1-to-1. We haven't changed anything. And then second, we call something that's called a linear stretch. If we're trying to bring out sort of the darker, features, we can do a linear stretch, but we see that we've completely lost the difference between the light gray and the bright white, and even the dark gray. And that's something we don't want to do. We don't want to lose information. So that's why we end up doing something called a nonlinear stretch for astrophotography images. And that's where we're bringing up sort of those darker details, but we're maintaining our brightest points. And that's what we're doing here. Well, this is actually something that you don't want to do. This is a linear stretch, and that was that middle example that I showed you, where you are bringing those details near the background, but you're completely saturating the brightest points. You're losing that information, you're clipping it, no good. Okay. Oops, too fast. This is exactly what we want to do. This is the nonlinear stretch that we saw. You can see the histogram now is nicely centered. It's crossing all of these different values. It looks very nice, and we're seeing all of that faint detail before, but we're also preserving those brightest values, which is exactly what we want to do. And so when you're making an image like the Carina Nebula, you have to do that to all the different filters. And we'll talk about filters in just a second. But this is it unstretched, straight from the telescope after it's been calibrated. And then this is it stretched. So we're bringing out all those details separately in all those different filters. Okay, so we went through stretching. Now we have to assign the colors, and we call this chromatic color. So I have a video that is showing the mid-infrared instrument. And this is just going to show you sort of how light travels into the instrument. So sometimes there's a misconception that these images start off in color, but they start off in black and white. And that's actually how your smartphones work too. You collect specific channels in red, green, and blue, and on the fly it makes a color image. And so it's essentially the same that we're doing. We just have a lot more filters to work with here. So the light gets redirected into this mid-infrared instrument, and then it gets directed to a filter wheel. And that filter wheel is collecting very specific wavelengths of light, which we then assign colors appropriately according to its wavelength. And then it gets picked up by the detector, and we get our image. And that's all we need for that guy. So we're done with this. Just in case you didn't know, Issa made the video. Okay. So that's all well and good. So how does that work when we are talking about infrared light? Well, we just apply what we know about visible light. So, for instance, in visible light, we perceive the shortest wavelengths as bluer and the longest wavelength as redder, and in between green. So we have sort of the same color channels as our phone do, red, green, and blue, to make our full color image, but in our brain. And we do the same thing to infrared light. So we use that same relationship where shorter is bluer and longer is redder. And so basically we're just mapping those colors into the infrared, or shifting the infrared into the visible part of the spectrum. So we're going back to our Carina Nebula, where we have these different filters, and we're assigning them appropriately in chromatic order so that the bluer color corresponds to the shortest wavelength. Here it's the 0.9 micron filter. And then we have our longest filter, which is 4.7, but it's yellow instead of red. So why did we do that? That's a little confusing. So we're not actually breaking any scientific rules here. The reason why we do this is, for one, 4.7 actually can be observed in the 2.1 filter. And that's because it's a specific emission that captures really hot hydrogen gas, something that's really important, and it's important to see. So if we just assigned it red, just like the 4.4 micron filter or the F44W filter, then we would completely miss it. It would be completely lost in that rest of the dust. But it's really important because it's showing off these jets from these young stars that are embedded in this dust. So we have to make those decisions. Okay, now before we combine that all together to make our full color image, we have to remove some of the artifacts. And those are just things that are introduced by the detector, or the electronics of the detector. So for instance, we have these striations that kind of might be hard to see, I don't know. But there's some banding errors that happen that we have to remove. There's also those dark cores of the stars. You know, stars don't have dark cores. That's just something that's introduced by the calibration pipeline. If if you can remember that first frame that we saw, it actually got saturated. So that means that that information, we can't get more information after that. So scientists can't perform any sort of analysis on these stars. That's all it's doing. So the black just flags that. It's a pain for us, though, to go back in and fix that. But we do that before we proceed, and then we can make our full color image. And this is our initial color image. So it kind of looks amazing. From the get-go, the data is great. It's a little bit teal, and it's a little bit red. But this is where it becomes a little bit more of a photography process. And there's not one point where it goes from objective to subjective, but we're constantly weighing the two in our process and letting the science sort of reinforce the art, and vice versa. So as I say that, there are aesthetic principles, though, that we consider in all these images, things like clarity, of course, because we want to show off the different details that we pick up in each filter. And of course, color is very important in doing the same. And composition, because that gives you a certain feel, and it can help you understand what's happening and the mechanisms that's happening in this object even more. So I'm going to return back to the artifacts that we were looking at, but there's one that we kept, and those are the diffraction spikes that I was talking about before, those 8-pointed stars. Why do we keep those? Well, there's a couple of reasons. One is we haven't developed like a great algorithm yet to remove them if we wanted to, but we don't remove them from any of our sort of images, like Hubble or any other ground-based telescope, and that's because they act as like a signature. So you look at this image, you know it came from Webb, and it's 8-pointed stars. You look at a Hubble image, it's got those 4 really crisp diffraction spikes, you know it's a Hubble image. And also, when you look at something like this, you know it's a space image. It's got sort of that etherealness, that whimsicality. It feels like, you know, twinkling stars, and that's how we see space. And another thing we've decided, you've probably seen the Carina Nebula mainly in this orientation, even though north-up orientation, the astronomy convention, is the one on the right. Even though there's no true north-up in space, so it doesn't really matter too much, at least on an aesthetic side, why did we decide to put it in landscape? Well, there's a lot of reasons for that. One is, aesthetically, it looks better, the weight of having sort of this mountainous region on the bottom, it just feels more natural. But also it acts as like a context, a parallel to something that we're used to seeing. And actually, this parallel helps us understand what's happening in this image more, because this is a mountainous, I mean, it looks like a mountain, it's just really dust that looks like a mountainous region that's being eroded by these really hot stars, and you can kind of form that parallel to mountains that we are used to seeing that are being eroded by weathering, by rain. Okay, so after we have combined this image all together, again, it becomes more like a photographer, a process of photography. And so we want to start really reinforcing, again, the details in each of these filters. And we also need to color balance the image and white balance the image. It's really difficult to do that when you have a nebulae, because you don't really have sky that's just dark, and that's what you use to really neutralize your images. So you do have to do things a little bit by eye sometimes if you don't have the luxury of doing like photometric calibration or using sort of the colors of stars to help you out, which you can't really do when you're doing Webb or Hubble images because they're just such small fields of the sky, there's not a lot to compare to. But we do our best, and we definitely use the core of the stars to help as our white balance, and we go from there. And then it's just a matter of making things feel more organic and also, again, emphasizing the science of this image. So I've sort of shifted this image. Everything's the same. The filters are the same. The color is the same. I just shifted a little bit to the blue because I'm trying to get more of that complementary nature between the orange and the blue, something that feels more like Dune, something more natural in sort of a sky. But also it helps reinforce the difference here of this dust, this dense dust, and this hot gas. And that's really what's happening here, as well as these bright stars in this star-forming region. Now, the nature of image processing, sometimes you can get a little carried away. And so this is one of those examples where I felt like I went too far. It's a little too saturated. Even though I didn't touch the saturation, I was just messing with curves. You get lost in the pixels and trying to bring out everything out. And this is what my colleague and I call overcooked. So we need to take it back. But at the same time, we're working very closely with scientists. So this is a very iterative process, and I'm not just kind of alone in my office going rogue, doing whatever I want. I'm listening, and we're making sure we're really showcasing the science as best as possible. So I'm talking with the scientists at this stage, and they're noticing that even though that gas sort of in front of the mountain is like a nice feature, it also sort of blocks out the detail in the dust. And they want to see more of that structure and 3D nature in that dust. And so that's what I end up doing. So we'll flip back again to the saturate and then a little bit more calm down. And then I'm bringing the local contrast into that mountainous region again to showcase the stuff that the scientists care about, which is important because we're discussing science. And then I think I flipped that really quickly, but after all that's said and done, we get together with the team to make sure everyone gives the okay, and then this would be the final release image that would go out, that's sort of like a more cohesive look. Okay, so I was talking specifically about the Carina Nebula and star-forming regions, but of course it's not a one-size-fits-all, and every object deserves a different approach, or even every data set deserves a different approach. This is another star-forming region on the left here. That's the Tarantula Nebula, and we have a star cluster too, and we had 6 filters available, but we only end up using 4. And you'd be like, oh, well, you got 6 filters, isn't more better? And sometimes it's not, because it's kind of like throwing a bunch of paint. Like, sometimes it just becomes gray or dull or, washed out. And what we want to do is, again, emphasize the different details in the filters. So you have to select filters discriminately in order to showcase that. And that's what's happening here, is we have 4 different filters instead of the 6. And we also have a special filter, or a special technique that we're doing here. It's called continuum subtraction, and all that means is that we have this smaller filter range, this 3.3 medium band filter, that's actually showing a specific thing, polyaromatic cyclic hydrocarbons, which is basically a fancy name for soot. But we care about it and we want to see it. So if we subtract like a wider wavelength that's next to it, either right above or right below, we can just focus on that soot. So that's what we end up doing here. And that will really help bring that out in the final image. So let's remove the soot for a second. And let's just walk through this image where this is sort of the initial color composite, kind of washed out. We have some color casting, like a green cast. We need to start getting depth in here, really seeing the stars and separating the stars, the dust, the gas, and that's what we are doing with a lot of curves adjustments and a lot of other fine details until we get to a good stage where we can add that filter back in, the soot. And you can see it adds it's a big difference. It really helps bring that feature out. And that's exactly what we want to do. If we didn't do the continuum subtraction, this could probably be just like orange cast and fuzzy. But we really want to focus on those details. And that's the Tarantula Nebula. This is the Tarantula Nebula in the mid-infrared. I've been focusing on the near-infrared camera. Sorry, Miri. Miri's great as well. We just focus on the near-infrared particular because it has such high resolution. But this is the mid-infrared image, which is just as beautiful. You use chromatic ordering in the same, but it is a bit different. Color balancing and things like that is a bit strange because it's unlike anything we've ever seen. It's the bones of these things that we're not used to. Very colorful because it's radiating in these different dusts, forms of dust. So very unique, but also a lot easier to work with because much smaller in size. So that's something. And then we also have deep fields. So deep fields are unique because we like to do something called stacking these different filters together. So we have 6 different filters. Instead of using the 6 alone, we actually stack the 2 closest together to form our color channel. So 2 that are close together, 2 of the shortest make blue, medium make green, and then 2 of the longest make red. And the reason why we do that is because color separation and showcasing a deep field is really important in showing off the science and why we look at deep field images in the first place. And that's because we want to get an idea of distances. This is stuff that's far away from us, that's redshifted. And so if we can squeeze out that color separation as much as possible, that's what we want to do. And so you can see here when you look at a deep field image, or in this one particular, which is the SMACS 0723, we can see that the reddest galaxies are either really dusty or they're really far away. And then we can also tell that those white areas or those blue stars are like very close to us, just by color, just by utilizing color in that way. And then we have Neptune. So this is a different way to process imagery as well. Now, when we're dealing with solar system object, it can be very different, especially if you're talking about like Jupiter or Saturn, which as you're taking images, they rotate. So you actually have to de-rotate the images for all the filters to align up. We won't get into that, but it's just showing you the differences in sort of all this processing. In the case of Neptune, we don't have to do that because it doesn't rotate enough for us to really notice, so we don't have to go through all that. But we do have to do something where we have to stretch different parts of the image differently in order to see everything at once. So we're highly compressing the dynamic range of this image. So we can get these background galaxies, which we only see with Webb images in terms of solar system imagery, and also we want to see these rings, which are faint. So we want to also apply a different stretch to that. And then we also have to apply a different stretch to the disk because it's so bright. And if we stretch it all the same, the disk will be blown out, the rings would be faint, and you probably wouldn't be able to see the galaxies. So that's why you end up doing that, because we want to be able to see everything at once. And then this is a protoplanetary disk. So nothing too fancy with this. It's also in chromatic order. But you notice that we do have the narrowband filter, the 3.7 or other. You probably could see better than I can. But that's an orange instead of red. And actually it's 470, right? I remember now. 4.7. And the reason why we do that is because, well, first of all, 4.7 falls within the 4.4 or microns, or the 444, because that's a wide filter. So we're not breaking, again, the convention of chromatic ordering, but also we need to select colors that work against the background of color. So the narrowband would work better on orange against red versus vice versa. So you have to think about those things to really bring out those details again. Okay, so I have been talking a lot about sort of these outreach images. And outreach images are, ones that we prepare that, the outreach branch of STSCI does a lot of careful planning to produce very aesthetic, compelling images. But the truth is, 90% of the work we do is on images like this, science imagery, because that's what Webb's supposed to do. It's supposed to do good science. And yes, it does create good imagery, but it's a lot more complicated, it's a lot more dirty. Like, scientists are not worried about these gaps between the chips. They're not going to spend their time, their precious proposal time on the telescope, dithering these images to fill in those gaps. So that's why it looks more like this. This is generally the data that we get. This is NGC 346. It's a star-forming region in the small Magellanic Cloud. And you can see there's chip gaps. There's some areas where there's more signal, so longer exposures, and then there's areas where there's very little signal, so lots of noise, lots of banding, so things that we have to take care of. And so I end up doing that, and there's a lot of ways you can do that. What we usually end up doing in something like this is we take the filter that's closest to us to fill in the gaps, if, of course, those filters don't have chip gaps. Luckily, on the Webb, the longer wavelength filters do not have that. The shorter wavelengths do, but not the longer wavelength filters, because Webb actually takes 2 different images through 2 different channels automatically between the long and the short. Pretty cool. Saves time. But as we can see, I have to reduce the noise, but also only in the areas that had less exposure time, and again, fill in the gaps, remove that banding that we talked about before, and all those artifacts like the star cores, which we have an algorithm in place to help us replace that, and etc. So we have to treat all of those individual filters again in order to do that. And so this is an image of us before we make those changes. So before we clean every individual filter, this is what you see. You can see the background variations between the filters. You can see where there's better signal and less signal, where there's banding. You can see in blue where there's some chip gaps, where we have missing data. So we got to clean that up in all of the filters. And then we finally get something like this. This is our initial color composite. So this is, again, where we start looking at it more of a photographer would, and we start, color balance the images, white balance the image. We can definitely do that in this one. We can definitely neutralize the background in this one because we actually do have actual sky, which is nice. So that makes it easier. And then really it's about remembering the story that we're trying to tell with this image. What is the science? What are we trying to emphasize? So this has a lot of hydrogen. It has hot hydrogen gas, ionized hydrogen, and it has molecular hydrogen. And we want to separate that, showing these different colors that represent these different forms of hydrogen. And so, the scientists can look at it and really pick it up, but it's really for, everyone to be able to understand it. So that's all I have for you guys today. Really, this is all about making imageries that are not just compelling, but obviously informative. So we're always leveraging art and science in order to produce this and get people engaged. So thank you for coming, guys.